Hi, in this video we will learn testing a claim about a mean, and the goal for this section is to conduct a formal hypothesis test of a claim about a population mean mu. Now recall that the best point estimate of the population mean is the x bar. This is from chapter 7, which is the sample mean. Now we can use either the p-value methods or the critical value methods that we discussed in the last videos to do the testing for this section. And for the mean, there are always two cases. The first one is we don't know the value of sigma, and the second one is when we know the value of sigma, and sigma is the population standard deviations. And usually in the real world applications, we won't know the value of the population standard deviations. But if we do know that, then that is the second case. So there are two cases. If we don't know the value of sigma, which is the population standard deviations, then we use the student t distributions. And if we know the value of sigma, then we use the normal z, like we did for the proportions in the last sections. And the requirements are very simple, and they are similar. We need the simple random sample n for the two cases, right? So either you have to get simple random sample, and then the second requirement is that we need a normally distributed population, or as long as the sample size is bigger than 30, then we are good. So either that we get the sample size is bigger than 30, or we need a normally distributed population. So either one of the two here, and then simple random sample. So this is one requirement, and this is another requirement. One of the two here, either one of the two here, then we are good with the simple random sample. And the test statistic that for the unknown sigma is the student t, and we follow the formula that we saw from chapter 7. T naught equal x bar, the sample mean, minus mu naught. This is the population mean, and over s divided by square root of n. S is the sample standard deviations, and n is the sample size. So all the notations are labeled here. And we can use either table 83 or technology from the TI 83 or 84 plus to help you to find the test statistics. And for the case of the normal z, the test statistic follow this formula: z naught equal to x bar subtract mu naught over sigma over the square root of n. Now, because we do know the value of the population standard deviation sigma, then we use the sigma instead of the s, which is the sample standard deviations. Because we don't know the value of the population standard deviation, that's why we use the sample standard deviations in this case. And also there's a note here. Sometimes that the sample size of 15 to 30 are sufficient if the population has a distribution that is not far from normal. So there's no fixed rule that there must be a certain number of sample size, as long as that all the data are not far from the normal. 15 to 30 sometimes are good, but just to make sure, we do require that the sample size is bigger than 30, or you need to have a normally distributed populations in order for we to use the test statistic follow the two cases here, right? So this is just to make sure that it's always true all the time. Okay, so again there are two cases, two methods. The first one is the p-value methods, and the second one is the critical value methods. And normally we use the p-value methods because a lot of the technology they display the value of the p-value. And there's a few simple step here. The first one is when you need to determine the null and the alternative hypothesis in one of the following three ways. So again, the same thing with the proportion. There are three ways: two tails, the left tail, the right tail. For the null hypothesis, the mu is always equal to mu naught, and mu naught is the sum value of the population mean. So the null hypothesis always involve the equal sign. So mu equal mu naught in the three cases here. And for the two tail, it means that, or the alternative hypothesis, it means that the mean is not equal to mu naught. So not equal is two tail, less than left tail, greater than or bigger than the right tail. So it's pointing to the left, it's left tail. It's pointing to the right, it's the right tail. And the null hypothesis always includes the equal sign here, here, and here. And then we select a level of significance alpha. Alpha is the probability of making the type 1 error. Remember from section 8.2, the type 1 error is when we reject the null hypothesis when it is actually true. Okay, and this depends on the seriousness of making a type 1 error. And usually the common choice for alpha is 0.05. Now for the p-value methods, we compute the test statistics that we saw earlier here. And then after that, if T0, we use T0 if unknown sigma with n-1 degree of freedom, and we use the Z0, which is the normal Z distribution, if we know the value of the sigma. So there are two cases. And then n-1 is again the same number of degree of freedom that we talk about from chapter 7. And we use table A3 or A2 or technology to determine the p-value. So for the case of the two tail, right? The two tail. So because we have two cases, either the student T distribution or the normal Z. Therefore, I have two cases here. The upper diagram here is for the student T distribution, and the below here is the normal Z. And for the two tails, the graph here, it is symmetric. So all you do is you just have to find the area of one tail and then just multiply that by 2. So the sum of the area in the tails is the p-value. Or the left tail, we only consider the area on the left side of the test statistic, which is the p-value. And then for the right tail, we only consider the area on the right side of the test statistic T0, and that is the p-value. The same thing to the Z, 2 times any of the one area on the left on the right, and then for the left tail, only the area on the left of the test statistic Z0, and then the right for the right area for the test statistic Z0. And yeah, we can use the TI 83 or 84 plus by using the TCDF functions for the student T or the normal CDF function for the Z distribution. So for the student T distribution, we use the T CDF. For the normal Z, we use the normal CDF. And you can find them on here. So let me turn on the TI-83. So all you do now is just go to second and then vars to get to the distribution. And then for the student T, we use the TCDF, the option 6. And for the normal Z, we use normal CDF. CDF stands for the cumulative area to the left of that. Okay. We will go over the example with this one later. And again, after you get everything, the p-value, if the p-value or the area here it is less than the alpha or the significant level, then we do reject the null hypothesis. If the p-value is bigger than alpha, then we do not reject the null hypothesis. Now, be careful here. We do not reject doesn't mean we accept the null hypothesis, right? It's very similar to the case that in the court system, when you say a person that is not guilty, doesn't mean that he or she is innocent. So in the same ways here, we say that we do not reject the null hypothesis, but it doesn't mean that we accept that. The second case is when we use the critical value method. So I repeat the same process of step 1, 2, 3. And then instead of finding the p-value method, I use the table A2 or A3 to find the critical value instead of the p-value. If it is a normal z, then the critical values for the two-tail case is the z alpha over 2, because alpha is one of the area, but now we have two tails, so we need alpha divided by 2 alpha over 2, and it is symmetric, so alpha over 2 for the right and minus alpha over 2, z alpha over 2 to the left for the two tails. And then for the left tail is just minus z of alpha, and the right tail is just z of alpha. The critical region is the one on the right of that, and then for the left tail is on the left side of that, and then the two tails on the left and the right together. And then we compare the test statistic. If the test statistic lie inside inside the critical region, then we do reject the null hypothesis. So for example, for the left tail case, if the test statistic z0 somehow less than minus z of alpha, which is inside the region of the critical region, then we reject the null hypothesis. So if any of the test statistic is inside the critical region, we reject the null hypothesis. And then the same thing for the student t's. If that is inside the critical region, then we do reject them. Reject the null hypothesis. Alright, so then there's a special note here when working with a small sample size. So again, we need the sample size to be bigger than 30 to make sure that we can apply the test statistic equation from the table above. If somehow that we get a sample size less than 30, this is a small sample size case, then we must verify that the sample data is coming from a normally distributed population. Make sure we check that, and we can do this by using a normal probability plot or the normal quantile plot. And if the data they display a straight line on the graph, then we assume that yes, the sample data they do come from a normally distributed population. And we can do that by we can display the normal quantile plot by using the tool in the tier 84. So you go to second stats plot, so second stats plot here, and then turn on the plot number 1. Make sure you turn it on, and then choose the type for the last case. This is the normal quantile plot, and then enter the data list to be the list that you store the data, and this will plot the observations of the data against the z-score. Okay, we will go over one example below here. So the first case, the first example, a simple random sample of the weight of 19 green M&Ms has a mean of 0.8635 gram and a standard deviation of 0.0570 gram. Now use a 0.05 significant level to test the claim. So this is the claim. The mean weight of all the rings M&Ms is equal to this amount, which is the mean weight required so that M&M have the weights printed on the package label. And do the ring M&Ms appear to have the weights consistent with the package label? So now we want to test the claim that the mean weight of all the ring M&M is equal. So this contains the equality, equal sign, right? Is equal to 0.8535. So this is the mean weight equal to this amount, which is mu equal to 0.8535. And if something that is equal to something in involving the equal sign, then that's become the null hypothesis. Then the alternative hypothesis is that you are testing for the mean weight to be equal to this amount. So if it is not equal, then that means it can be bigger than or can be less than, right? So either that this is equal or this is not equal. Then the not equal should be the alternative hypothesis. So the claim, the original claim was that the mean weight of all the ring M&Ms is equal to 0.8535. Then the alternative hypothesis is the one that is different from the original claim, which is not equal, because we claim that this should be equal. If this is not true, then it should not be equal to that number here. And then from the given problem, we see that there's 19 ring M&Ms, right? So that is the n, the sample size, and alpha is 0.05 because they said that we use the 0.05 significant level. And also we are given the mean of, so 19 sample size, 19 data points, they have a mean of 0.8635. This is the sample mean, so that is x bar. And also the standard deviation of 0.0570 right here, so that is s. Now we check the requirement. This is a simple random sample, so the first requirement is good. The second requirement is not good for now because n is 19 is less than 30. So we need to make sure that the population is normally distributed or not. Okay, so the way we do that is that we check the data on the normal quantile plots. Now these are the given 19 data points. So this table is given to you. So the way I do that is, first I need to store the data in the calculator. So we have to go to Start and then Edit, hit Enter, and then I choose the column L1 to store the data. So I have to enter all of them: 0.925, 0.914, 0.881, 0.865, 0.865, 1.015, 0.876, 0.809, 0.865, 10 more, 0.848, 0.940 right here, enter, 0.833, 0.845, 0.852, 0.778, one more 7, 0.814, 0.791, 0.810, and the last data point is 0.881. Okay, so we need to plot this one in the normal quantile plot. So the way I do that is I got out here second start plot, and then make sure I pick the first one, enter, make sure I turn it on, click enter, and then the type, so we right arrow until the last one, hit enter, and then we know that the list, the data list, we store the data in A1, so A1 is good. We plot against the x-axis, that is good, and the mark is just a square, the little square, so that's good. So go to zoom and then choose the zoom start number 9 option, right, and then hit enter. Okay, so let's compare that to this data here. So yes, we do got the same thing before here. So this data does give you a straight line, right? So the normal quantile plot exhibits a straight line. So it seems like it's coming from a normally distributed population. So that's good. So we are good for all the requirements. Now it is time for us to do some testing. So the null hypothesis is mu equal to that, and the alternative hypothesis mu is not equal. And we know that this is the sum value of the population mean. So mu naught and mu naught is here, right? And the test, because this is the unknown value for the population standard deviation, sigma is not known in this case. That's why we have to use the student t. So go back to the table in the beginning. If sigma is not known, then we use the student t, which is t naught in the test statistic, this formula here. And then I use that table to use the formula t naught equal to x bar, the sample mean, minus mu naught, which is right here, over s. We also got s above, and n is 19 sample size, and then do all the division here, simplification, then you should get 0.765. And because this is the not equal, so it's two-tailed test. So two-tailed test, we know that this is 0.765 is the test statistic, and that's one more, which is minus 0.675. They are the same value because the graph is symmetric. So all you want to find the p-value, which is the area, the red area. So all we do now is we find the p-value, the p of the area to the right of 0.765, and then multiply that by 2 because they are equal. So to find the area, the red one, we use the second verse to use the TCDF. TCDF is the commands for finding the cumulative area to the cumulative area of the student t distribution. So if I plot the command for that is that the first spot is the lower bound, which is 0.765, the lower bound. The upper bound is the next spot. So we go from here to all the way to the right, so very large number, so I just put 10 to the 99. You can just put very large number, and 10 to the 99 is good enough. And then the last spot is for the degree of freedom. We have 19 to 19 minus 1 because it's n minus 1. And then this is just one area to the right of 0.765, the red one here. And multiply that by 2 because this is a two-tailed test, and we get a p-value of 0.454. And because this is bigger than the alpha, which is 0.05, if it's less than alpha, then we reject the null hypothesis. But in this case, this is bigger than alpha. We do not reject the null hypothesis. That means we don't have enough evidence to say that this is not correct, right? So we do not reject it. And let's try here. If you use the TI-84 plus, then use the second var to get to the distribution list here, and we pick the TCDF, and you enter the lower, the upper, so which is 0.765, the upper 10 to the 99, the real freedom which is 18, and then paste this one into the commands. So the TI-84, it is good in a way that it gives you the input the list, so you can enter the data, and then it will automatically input that into the command. It should be here, and then enter, and we multiply that by 2 to get to the p-value, because this is 2 tails, and that gives you 0.454, which is right here. So we don't have enough evidence, or there is not sufficient evidence to warrant the rejection of the claim that the mean weight for all of the range M&M is equal to 0.8535. If we fail to reject, we do not reject, that means the range M&Ms do appear to have the weights consistent with the package level. Because this is the claim, this is the one they claim on the package level, so we do not reject it. That means we can say that they do appear to have the weights consistent with the package level. Okay, now we just went over a whole process of finding the p-value by hand, but the TI-84 is very awesome. They can do this completely by the system here. So if we want to test for, you want to find a p-value, so all you do now is go to stats, and then go to the test list, and then we pick what? We pick the in this case we pick the t-test, because we are using the student t distribution, so you have to use the t-test, the second one, hit enter, and then we use the data from L1. So we do store the data in L1. So I pick the data. Mu naught is the value here, right here. So that equal to 0.8535. So let me input that. 0.8535. We had the data in L1. And then in this case, mu is the alternative hypothesis, and this is the 2 tails, so not equal sign. And then enter, 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 and that's good. And hit calculate, hit enter, and then they display you the t-test, everything that you just did by hand. So this number here, same thing, right? We got the same thing. So this t here is the test statistic, t naught, and this p here is the p-value, which is the same thing, very similar to the one we found here, 0.454 and 0.453. So it's just because of the routing error. All right, so that is the end of the section, and we only focus on the p-value methods in this case, because many technologies that we are using now, they do display the p-value, and it's very simple to use that for this section. Okay, thanks for watching.